Hi everyone. So let's start from where we left. So last week we saw a couple of examples of strongly coupled field theories in dimension 2 and 3, and we saw that we can say something beyond perturbation theory using the Largen expansion. And that allowed us to discover some interesting dynamics, including some interesting massive phases with the resonances and bound states, and also the existence of interacting conformal field theories. And we said that one of our motivations to study these theories is that they can be used as toy models for strongly coupled field theories that we care maybe more from a phenomenological point of view, such as gauge theories in 4 dimensions. So now we want to continue our examples with something which is even closer to 4-dimensional gauge theories, in that it's just a lower dimensional version. So the next example we are going to discuss is QCD in 2 dimensions, and this is also called Toft model. And it's discussed in the famous paper from 1974. And we're also going to use here the Largen expansion. So let's start by writing the Lagrangian. So this is an abelian gauge theory. So we have our gluons, and they interact with some flavors of Dirac fermions in the fundamental representation of the gauge group. So you see it's literally QCD, just in lower dimensions. I will specify in a second what are all these indices. There are some mass terms. Okay. So here, here this letter I that I put on the fermion is a flavor index. So we have NF Dirac fermions, and they are in the fundamental representation of the gauge group, which I should have written already here. We take the gauge group to be SUN. Okay? So it's an SUN gauge theory. Now, what else do I want to say? A and B instead are color indices, okay? And they go from 1 to n. Another important thing that we immediately notice is that this coupling, G squared, right? We already mentioned it last week at the beginning, that if we write down gauge kinetic terms in dimension lower than 4, then we need to stick some coupling in front, which is dimensionful, right? So in this case, what's the mass dimension of this guy? So F mu nu is dimension 4. So since we are in 2 dimensions, this guy is an energy squared. Okay, so already classically, without computing any loops, this guy is clearly a relevant coupling, relevant interaction. So asymptotic freedom is for free in lower dimension. The relevant interaction, which flows to strong coupling, in the IR. Okay. And let me also unpack the notation. I mean, I guess all of you are familiar with this from your QFT class, but just to be on the same page, let me just write it down explicitly. So this is what I'm taking. So our field strength contains the usual anti-symmetrized derivative and the commutator. And these guys, you see, we can denote them depending on what is more convenient for what we are doing. We can either denote them with two indices, okay, like matrices, or we can just pull out the generators, and then we are going to use this A, which is an adjoint index. Right? So, and then just some useful formulas. Just some useful formulas are these. We normalize our generators like this. They satisfy these commutation relations, where these F are the structure constants. We take them to be Hermitian. Okay, that's why we have an I here. And finally, let's spell out explicitly what is this covariant derivative. So what is the covariant derivative acting on our fermion? It's just the normal derivative plus, oops, actually minus convention, this is minus I, A mu, A B, psi I. Okay? So this is perhaps all familiar from gauge theories. And so what is going to be our goal in going forward? Our goal is to understand, like we will see that in the taking the large n limit, we will be able to actually compute, or let's say, maybe not compute, but find a way to obtain the mass of the mesons in this theory, okay? So which is something that it's very hard to do in 4-dimensional QCD, even at large n. And one thing that it's perhaps not so surprising that is going on in this theory is that it's still true that the quarks, let's call these fermions our quarks, it's still true that our quarks are confined inside some hadrons. This perhaps not so surprising, because if you look at the way the classical potential works in 2 dimensions, just at the classical level, you see that you have a linearly rising potential. But of course, again, this classical approximation is only reliable at weak coupling. It's just less shocking, perhaps, compared to 4 dimensions, that the quarks would be confined inside the hadrons. This doesn't make it any simpler to obtain some quantitative prediction for the masses of the meson, so that's our goal. Now, you see that there is a big difference already at this level compared to the theories that we discussed last week. And the big difference is that we have this guy floating around, which has two indices, okay? So last week we only had self-interacting fields which had one index, which we call the vector degrees of freedom. And now we have this guy, which is a matrix. So we might be at first a little bit desperate. So let me explain a little bit why we could be desperate. So let's draw some diagrams. Example of diagrams. That dominate. So a good starting point, if we want to start seeing that the quarks form bound states, is to start studying the scattering, right, of the quarks. So for instance, let's look at what happens if we try to scatter a quark and an anti-quark. Okay, so they come and they go in that direction. And let's draw an example of a diagram that would be dominant at large n. So I will draw it, and then I will convince you that it's a dominant diagram. And this is just one possible example. So let's consider some monster like this. So you see, as you're familiar from your QFT class, expanding this trace f mu nu term, we are going to get both cubic and quartic self-interactions for our gluons. So let's just draw some example. You see, I can start connecting these lines of the gluon in a lot of different ways. Now my goal is to convince you that this monster is dominant at leading order at large n. So let's do some counting. Let's do some counting at large n. And for that, you see, it's convenient to actually remember that this guy has two indices from 1 to n. So I'm going to use what is called double line notation, okay? So I'm just going to write the propagator of this. Instead of a wiggly line, I'm going to write it as two lines, which allow me to easily follow the contraction of the indices, okay? So how does that guy look like? You see, I'm going to here spit this double line, then the double line goes, connects in this way. Of course, we could just sit down and do a formal derivation of the counting, but I think it's more fun to just see an example and then say that it works in general. So we have this, and then what did I draw there? Something like this. Okay, whatever. I just picked some diagram that look like this. Right? So with my double line notation, it takes this form. And now let's count. So the first thing that we made manifest with this double line notation is that we can easily count how many closed loops of our index we have, right? So how many do we have? We have 1, 2, 3, and 4, right? And then, okay, it's not actually in the normalization that I chose, but by rescaling the gauge field, we know that to the cubic vertices, to the cubic vertex, we associate a power of G, the gauge coupling, and to the quartic one, we associate a G squared, right? So let's do the counting. How many cubic vertices do we have? And also the cubic vertex with the Dirac fermions also cost us as power of G, right? So in total we have, let's use colors. So the cubic vertex, this color is not very clear, but okay, we do what we can. So we have 1, 2, 3, 4, 5, 6, 7, and 8, okay? And then let's do the quartic one. We have just one in this, and this costs us a G squared. So in total, we get a g to the 8 times g squared, and then we have 4 powers of n, right? Times n to the 4. Correct? So this becomes a g to the 10 times n to the 4. And now, what is the scaling we want to take? So the scaling we want to take is the famous 't Hooft scaling, in which g squared times n is kept fixed. Okay, we call it lambda. G squared times n is kept fixed. And then you see what you get here is a lambda to the 5 divided by n, because you get 5 powers of n from this, and we had 4 in the numerator. So the Largen counting of this diagram is just that this diagram contributes at order 1 over n, okay? But you see, this order 1 over n is exactly the same as the simplest possible diagram that we could draw, in which we just have 2 quarks going and exchanging a gluon. If you think about it for a second, so the simplest possible diagram, the first diagram in perturbation theory would be this one. First one we would consider would be this one, right? And this is just equivalent to this, if you want to make explicit the Largen counting. And you see here we just have a g squared, which is a lambda over n. We don't have any closed loop, right? So this complicated monster we had there contributes exactly at the same order as that. So it seems like we are forced to resum all the planar diagrams. Without. So you see this word planar comes from the fact that the salient feature of this diagram over here, which made it be dominant in this Largen expansion, is that you can arrange your closed loop as basically a tessellation of this strip between the two quark propagators. You see, we just had just built some tiles, and these tiles cover the strip. And all the diagrams of this form, in whatever way you arrange them, they are always, you can convince yourself easily that they will contribute at the order 1 over n. And you see, now we are a bit in trouble, it seems, because this is a much more complicated structure than the simple geometric resummation of bubble diagrams that we used last week. So just to be leading order. So what the story seems to be is that at leading order we get all the diagrams in which I can fill this strip. And then there is the nice story of the topological expansion, which I will not review, but you can find it in many textbooks, which is what also 't Hooft discovered in a paper not so much before the one we are discussing. And so, for instance, it's a bleeding order, we would have to consider all diagrams which can be arranged on some surface like this, okay? And so on and so forth. Okay? Now, what I said just now is that already doing this, which we will be happy with, it's very complicated. It's very complicated because we don't have a nice organization principle to sum all these diagrams. So what allows us to proceed is the following. So why can we actually make some quantitative predictions in this model? So the story would be basically this if we were doing QCD in 3 dimensions or higher. We would basically stop here and maybe do some qualitative considerations. We could continue doing some qualitative considerations based on this, but we would not go further and actually resum diagrams and obtain some quantitative prediction. Instead, in 2D, we can go further. And what allows us to proceed is that there is a particular choice of gauge. Yes? Yeah. This is supposed to be the drawing of some hole in the surface.
This is the genus of the space-time manifold, or?
No, sorry. This is what I was saying before is that you see the leading order one. It's like you have to arrange your double line graph in such a way that it's a tessellation of this strip. Okay, while the subleading one will be a tessellation of this more complicated thing. So it means that you will allow also some of these gluon propagators to cross each other sometimes. Okay, that you can do when you're arranging your diagrams on top of this surface. Okay. So what allows us? Yes. So let's see. This should give you a further 1 over n squared suppression. Okay? So if we said that this guy was 1 over n, this is going to be 1 over n cubed and so forth. Okay? Well, there are also other things you could do, which is to add punch holes inside where you make your fermions run. These give you just a 1 over n suppression. Okay, but okay, let's not go into that. Now, what is the thing that allows us to go further and make some quantitative prediction? Is that we have a particular choice of gauge in which the gluon self-interactions are 0. Okay, the gluon self-interaction vanish. So that's a bit weird, right? So we might ask, how can this even be possible? And this is possible because there is no propagating degree of freedom associated to the gluon. Okay, so calling it gluon is actually a bit of a misnomer, but okay, I will still use it. No propagating degrees of freedom associated to a gluon. Okay. So what's the idea here? The idea is that if you look at the Maxwell equation in generic D, right, in order to have some propagating degree of freedom, you're going to have your wave moving in some direction, and then the polarization is going to be transverse. But here we have only one space. We only have one space dimension, so there is nowhere to be transverse. So there cannot be any wave associated to our Maxwell or Yang-Mills, if you prefer, kinetic term. And as a result, this A mu field doesn't create any particle, okay? There is no particle, even at weak coupling. You see, if there would be some particle, then it would be extremely weird that we can just set to 0 the interactions by a choice of gauge, because you see, if there would be a particle, then we could consider some scattering, and this would be some physical observable, right, where we put our asymptotic state, and then it would be weird that we can just make it completely trivial, like this would be a gauge invariant thing now, and it shouldn't be allowed to just make it 0 by some choice of gauge. However, since there is no such an external lag, we are happy and maybe it's possible, and indeed it's possible. Sorry, can you say again? Glue balls. Yeah, well, there is also not going to be glue ball. Like if you just consider, so one way to interpret your question would be, what about if I don't put any quarks? Do I have some interesting spectrum of massive particles? And the answer is no, I don't have an interesting spectrum of massive particles, okay? Like Young Mills in 2D, it's a bit, doesn't have a propagated degrees of freedom, it's just a topological, not really topological, but almost, like it can be solved exactly. So yeah, the reason why there is some interesting stuff going on is because we have quarks that interact with the gluons. Okay, now which blackboard is due? This one. So let's convince ourselves that this gauge in fact exists. Self-interactions of the gluon. Okay, what do they look like? This is the same as what we read in Peskin for QCD in 4 dimensions. So there is a term like this, right? With the cubic term is this. It comes from the product of the commutator with the derivative, and we can write it explicitly like this. There is one derivative, and then there are these two guys, right? And then there is the other self-interaction. The other self-interaction is two commutators together, right? How does this look like when we open it up? This looks like a minus, then there is an F. I remember if I wrote explicitly, did I write explicitly what my convention for F mu nu is? Yes, I think I did, right? Yes, yes. F ABC, F D E C, and thus we just have A mu A nu B, A mu D, A nu E. Okay? Just to be super explicit. And now, what do we notice? We notice that here we have some antisymmetric combination of the two gauge fields, and same is true here. Okay, we have this antisymmetric combination and this antisymmetric combination. So these things are antisymmetric combinations of two mu fields. So in other words, they must be antisymmetric in the as well in the mu nu indices, right? Because we antisymmetrized in the adjoint ones. And now we remember that we are in 2 dimensions. So if you do antisymmetric combination of two fields, the only thing that they can be is something like A1, A2, right? Because there are only two components. And here I mean the mu, these are the mu nu indices, okay? The special, these are the space-time indices. Okay, but now you see, this seems very nice because we can just work in a gauge in which we set to 0 one of these two components, and then automatically we're going to kill all the self-interactions. So let's do it, and we're going to proceed from there. So choosing an axial gauge. Okay, axial gauge is the name that we give to the family of gauges in which we just set to 0 some components. So for instance, I don't know, I take A2 and I set it to 0. Both of the interaction terms trivialize. Okay, and in this way we are only left. So now let's go back to our strip with two quarks propagating, and let's see what diagrams we can draw now. So now the only things we can draw are of this form. We can take one guy and make it go all the way to the other line, okay? Or alternatively, it can go back to the same line, right? There is still the constraint of planarity if I want to be leading order at large n. So yes, I can add other lines of the gluon, but they should not cross each other. Otherwise, it would not be possible to write it as a tessellation of the strip, okay? So for instance, here I can do this, then I can add this, okay? These are fine because they never cross. Then here I can add as many vertical lines as I want. Okay, and I keep going. I can keep going. At some point I will stop because there is no point in keeping adding things. But okay, so you see, this gives you a flavor of the kind of diagrams that I will have. Okay, so now this makes me much more hopeful because I start seeing some organization principle in these diagrams, and I can hope to be able to resum them, right? So in particular, you see I have this, let's also use some color here. I have this structure over here, which is alternating with some other structure, which are these vertical lines. So it's much more tame kind of situation. So I have some, we should call them probably rainbow diagrams. Which are propagator corrections. For the fermion. And some what is called usually ladder diagrams. Okay, the ladders are this, I think it's clear from the drawing why they're called so. Is it clear from the drawing? Yeah, okay. Okay, so that's going to be our goal, to resum these two families of diagrams and get some quantitative predictions. So you see, here I said A2 equals 0, but actually that's not the way we are going to work. So let's just observe that more generally, this works for any choice of the type n mu a mu equals 0, right? We can just set to 0 the gauge field in any direction. Of course, there is nothing special about the axis 2 that I chose. I can choose any direction. And I want to discuss briefly, for this general choice, what happens when I do the gauge fixing, because maybe some of you might be wondering what happened to the ghosts. So let's discuss for a second what happens to the ghosts. So when I do the gauge fixing, what I need to do is there a question? N mu is just n is just some vector in R2. Okay, I just can pick any direction. Yes? If we are on a compact menu, you mean that it's gauge invariant, the holonomy? That's a very good question. Let me think. Well, I think you will be forced to add, you can still set to 0 like for small fluctuations, let's say, of the gauge field, but you will force to add some global, some degree of freedom, which is just the holonomy, and perhaps you can represent it by yes, you're right. Well, okay, for instance, if you want to do the thermal partition function in a non-compact space, you can still set to 0 the other component. Otherwise, I think you will have to add, so most of what we are doing now is not going to include the global structure of the gauge group. We're just going to do some, perturbative calculation. And for that, I think probably you're fine not to worry about the holonomy. Otherwise, probably what happens is that you need to add also some sum over the possible holonomies. Yeah, I haven't really thought about this, but I guess that's what you have to do. Okay, so yes. So I want to just for a second discuss. So of course, there is nothing special about 2, so let me just discuss this. And the reason why I want to call it like this is because eventually we are going to do some peculiar choice for this n. Okay, so for a moment, let's pick it general. So yes. Yeah, they will depend, but at the moment we haven't computed any diagram, right? I just told you what diagrams we have to compute. And in the intermediate steps, we are going to have something that depends on our gauge. But when we go to something which is unobservable, like the mass of the mesons, that hopefully will not depend. Otherwise, it means that we have made some mistake. Okay. Now, how do we gauge fix? So we had some Lagrange multiplier just to have a delta function of our constraint. And then usually what we do is that we add ghosts, right? And let's recall why this is the kind of ghost action that we are going to get. How do we compute the action for the ghosts? The way we compute it. So this is just a Lagrange multiplier that gives us the delta function constraint. And these are our ghosts. Okay, and then in the path integral, we're going to add some integral in B, some integral in C, and C bar. Okay. Now, I just want to remind you why this is. So the kinetic term how do we do it? We take the constraint. So in this case, is this guy. So this is the guy we are setting to 0, right? So then what do? We do a gauge transformation of it. We do a gauge transformation of the constraint. And let me call omega my gauge parameter. Let me put also, okay, so omega A is the gauge parameter. So we get something like this. And finally, we need to take a variation. We need to take a variation with respect to the gauge parameter, right? You agree? We need to take a variation with respect to the gauge parameter. So indeed, you see that we get something like mu times this covariant derivative. And that's what appears in our ghost kinetic term. Now, what is the good news? What are the good news from this? It's just on our constraint. You see what happens? If you take the covariant derivative, so let me just spell it out explicitly. So this is just d mu delta AB minus I f A B C A mu C, right? And now you take it and you contract it with n, but then you see what happens is that the gauge field just drops from here because of the constraint. Okay, it drops because of the constraint, so this becomes just an ordinary derivative. So another nice feature of this kind of gauges is that the ghosts basically decouple, and we can forget about them. We can forget about them. So okay, so we are very happy. Now let's pick wisely this vector n mu, okay? So it turns out that the best possible choice is to take this n mu to be a vector that squares to 0, okay? And in a second I will explain why. So the best possible choice is to take n mu equals 0. Okay? So it's a null vector. And this means that this n is going to be a real, can be a real vector if you're in Lorentzian signature, but otherwise it needs to be complex if you're in Euclidean. Okay? So the components, the associated components of the gauge field, so the ones along the direction of this null vector and orthogonal are the light cone components plus minus, which you see in Euclidean we need to take this combinations with an I in between. And in Lorentzian, if you do a weak rotation, this becomes just A1 plus minus A naught divided by square root of 2. Okay, so the weak rotation relates A naught to IA2. Okay, so finally I can announce that we are going to fix the gauge A minus equals 0, which is what is called light cone gauge. Okay, so why is that a particularly good choice? One reason that is immediately clear is that it has this nice property that under boosts, you see this A minus just goes to itself, okay, where alpha is the rapidity. If you would work in Euclidean, we would instead say that under rotations, A minus goes to e to the I alpha A minus, okay, it's the same thing. And so you see this, this gauge basically doesn't break any of the group that we have in 2D, of the space-time group. So while if we would have picked A2 equals 0, clearly we would have broken something, okay? So we do not break space-time symmetry. Because A2 or A1, they clearly mix with the other components under a booster rotation. Okay. So I hope you're convinced that this is a good gauge to use. Any question before we proceed? At some point, we're going to start doing a lot of calculations. Yes? Again, repeat. So in this case now, light cone gauge, it's easy to see why the gluon interaction vanished. So the reason, the way we argued that the gluon self-interactions would vanish was just because we had this anti-symmetrization, right? And that holds for any vector n we might possibly pick, no? Because we always can pick n and the orthogonal one, and we anti-symmetrize, and then, you see? That argument was independent on the particular choice of 1, 2, or any. Indeed, what I called 2 was completely arbitrary. Now, before proceeding and starting to do a lot of calculations, I want to, I would be very sad not to make this observation. Okay. So, I see, what do I want to say? So this trick only works or let's say this trick would not work with Yang-Mills kinetic term for the gluon in dimension bigger or equal to 3. And the reason is simply that you see what we did is that we had 2 components antisymmetrized, but in higher dimension we're going to have 3 components antisymmetrized, 4 components antisymmetrized. Sorry. Yes, I mean, we always have 2 fields, but they have more components, right? So we cannot completely set to 0 the interaction. However, there is an interesting additional possibility in D equals 3. And okay, and this is also associated to the fact that we said before that when we are in D3 or above, now there is going to be at least perturbatively a particle associated to the gluon, right? Because there are going to be propagating degrees of freedom. So indeed, we cannot just do a choice of gauge and we set magically to 0 everything. However, there is an analogous story which has the same flavor in D equals 3, because we have an additional possibility for the kinetic term. And this is the Chern-Simons term. Okay, so let me write down how this looks like. So we can write this kind of Lagrangian, which is a gauge invariant in 3 dimensions. It's very specific to D equals 3. So another difference between what we are doing today and what we did last week is that the theories that we studied last week very naturally are very natural to study, let's say, in a generic dimension, while for these things it's better to stick to some specific dimension and do the analysis. Okay, and here we have some epsilon, mu, nu, rho. Okay, so that's the thing that makes it special to 3D. And if you expand it out, taking the trace, this Chern-Simons term becomes something like this. So this is like the bilinear part which gives us the quote-unquote propagator. Well, even without quote-unquote. Give us the propagator, and then we have this interaction. So you see what's going on here. Now again, we have the interaction term between the gluons, which involved a completely antisymmetric combination of 3 fields. Okay. So in complete analogy with what we discussed before, so this is a completely antisymmetric combination. So we can set it to 0. Choosing a gauge of the form n mu equals 0. Okay. So we can consider in 3D theories of matter fields, scalars or fermions, interacting with gluons, in quotes, that have Chern-Simons kinetic term. And they are solvable in the same, like with the very similar techniques what we're gonna see. And they are solvable in a similar way. Everything okay? Something fell to what we are going to discuss. Okay, and so again in this series we will have to resum basically rainbow diagrams and ladder diagrams the same type. And an important thing is that, you see, again, what is going on here is that if we just have a Chern-Simons kinetic term for the gluon in 3 dimensions, again, there is no propagating degree of freedom associated to the gluon. So that's why, again, this magic is possible, okay? And in both cases, like in QCD in 2D or in Chern-Simons in 3D, what is going on is that this non-abelian field, this non-abelian gauge field, is just basically mediating a force between the matter fields, okay? It's not really, it doesn't have really any propagating degree of freedom associated to it. Okay, so summarizing, we can say that there are 3 levels of difficulty. So there are 3 levels of difficulty. So there is the case of self-interacting vectors in any D. And for this, we just have to resum bubbles. Okay, and we are happy. Then there is the intermediate difficulty, which is vectors with either Young-Mills gluons in 2D. Sorry, I should be clear. Like, remember that when I call what I call vectors here, I mean the vector indices of the large n of the. I mean that have an index that goes from 1 to n. Okay, so don't get confused between vectors in space-time. Here I mean vector in the internal symmetry. So vectors with Young-Mills gluons in 2D or with Chern-Simons gluons in 3D. And in this case, we need to resum rainbows and ladders. Okay. And then finally, there is the case of vectors with gluons in all other cases. And in this case, we have all planar diagrams, and we don't know exactly how to do it quantitatively. Okay, so these 2 we can compute. Well, in this case, this is, let's say, qualitative. We can draw some qualitative conclusions from the large n expansion. Okay. And indeed, I mean, we are not going to say much, but people studied in details this theory with Chern-Simons interactions in 3D, and you know, you can take precisely the theories that we studied last week, let's say the ON model or the fermions, with or without the quartic interactions that we studied, and you can just couple it to some Chern-Simons gauge fields that gauge the global ON symmetry that we had. And people doing that, they discovered all kind of nice phenomena. such as like dualities between bosons and fermions, and this theory even have some exotic holographic dual gravity, and interesting massive phases, CFTs, all kind of things. And but okay, that would take another course to cover. So for now, we are going to stick to the case of gluons of Young Mills in 2 dimensions. Okay. Okay. So now finally we start doing some calculation. Any questions so far? Okay. Otherwise, let's go ahead. So we said that we are going to set this to 0, and when we use this plus and minus indices, just to remind you that when you raise the index, you get a plus, okay, because the metric is mixes the plus and minus. So let's fix some notation. So this is going to be our x plus. We are going to go a bit back and forth between Euclidean and Lorentzian, but that's not a big deal, right? We just take the component 2 and we stick an I. And for lower indices, this is the opposite, at least according to my note. And when we switch to Lorentzian, this is going to become minus x naught, and the lower guy is going to become phi naught, okay? Good. And when we take the square of the vector, this is 2 x plus s minus. Okay, or in other words, x plus plus x minus. Okay. Tell me if something is not clear. Then let me also specify the gamma matrices for our 2D Dirac fermions. So they need to satisfy the Clifford algebra. So let me spell it out explicitly. We have this gamma plus squared and gamma minus squared are 0. So they're nice nilpotent matrices. And then the other entry of the Clifford algebra is this one, okay? Now let's write down our Lagrangian with this gauge. How does it look like now? It looks like this. Plus okay, so here we have gamma plus. Let's be super explicit since we have only 2 components, so it doesn't take too much to write them all down. And you see now I only have the interaction with A plus. Couldn't be otherwise because A minus was killed. And then we have also, let's consider adding some mass terms for our flavors. In principle, we could take them different, and then this will break our flavor symmetry. And for special cases, we're going to have some symmetry, some flavor symmetry. Okay? Now, what are the Feynman rules that we derive from this? Since I wrote extremely large, maybe it doesn't fit here. So we have our propagator for the gluon, which you can decide if you want to denote it with the wave or you want to denote it with the double line. And this just takes the following form. You see I need to go to momentum space, write the quadratic operator, and then you invert it, and you get g squared over k minus squared. Okay? So now I'm really sticking to my convention in which the g is in the kinetic term. Okay? Then we have the propagator for the gauge field, sorry, for the Dirac fermion. And this has flavor indices and spinor indices. And you do the calculation, and when you do the calculation, you find the following. Okay? This is just the familiar inversion of the quadratic term. One just needs to get used to see the usual formulas rewritten with the plus and minus indices. And then we have the vertex. So the vertex, again, you can decide if you prefer to write it with the wavy or the double line convention. But in any case, it is just I gamma minus. Okay? And you see, just don't get confused, there is no g here because the g is here, okay? It's in the propagator, so that's why there is no g in the vertex. Now, we can do a further simplification, which is the following. Our goal is going to be to compute diagrams like this. So we want to completely get rid, we want to get rid altogether of the fermion indices. So let's do it. So how are our diagrams going to look like? So we're going to have some incoming fermions, then some amenities like this. Right? Just giving some example here. And then at some point, they're going to go out, right? Now, so this is just using the double line notation. Now, what can we observe? We observe that, let's look at the spinor index structure of this kind of diagram, right? So we just have in every vertex here, we always have some gamma minus. All of these are gamma minus, right? And if it were not because we have this propagator inside, you see the propagator is what makes this thing survive, because gamma minus squared is 0. But luckily we have the fermionic propagator, so the gamma plus helps us to find something which is not 0. But eventually we get here, right? So here we have a gamma minus here. We have a gamma minus here. So what we can do is that we can just, to completely suppress the fermionic indices, we can consider tracing out our diagram, right? We can trace the fermionic indices. And now, here in principle, we could put a gamma plus or a gamma minus. So if we do the trace both with the gamma plus and the gamma minus, we retrieve all the information about the diagram. But you see that when we trace it and we insert a gamma minus, so this gives us 0. So the full information about Dirac indices can be obtained tracing with gamma plus. Okay. So now basically we are just going to have the structure of a gamma minus in each vertex, a gamma plus in each propagator, and so on and so forth. That's all we need to retain. And the same here. Also here we are going to trace with a gamma plus. Is it clear? Are there questions about this? So eventually we just have, if you follow of the spinor index, we just have alternating gamma plus and gamma minus, and that's the only thing that gives you a non-zero contribution. In the vertices, you're forced to put the gamma minus, so you know what to put in all the other parts. Okay, so if you follow this logic, you can completely get rid of these spinor indices and rewrite the following, let's say, simplified Feynman rules. So the simplified Feynman rules are, okay, the one of the gluon didn't change. We have a k minus squared. And now we just suppress the spinor indices. And here we pick simply the coefficient of gamma plus, okay? We just pick the coefficient of gamma plus. So we have delta ij minus I k minus divided by and the vertex, you just need to be careful about the factor of 2, but you can convince yourself that you need to stick a 2 here. Okay, just this comes from the 2 that we have in the Clifford algebra. Okay, so we are very happy. We already got rid of the spinor indices. Now we need to start doing the resummation. So first we're gonna resum the rainbow diagrams, and after that we're gonna resum the ladder diagrams, okay? Any question at this point? Yes? How do I get rid of what? The mass. It's because you see, if I have the vertices always have gamma minus. Sorry, yes, gamma minus. So if I put the identity, I just get 2 gamma minuses, and I get 0. So now we want to resum the rainbows. That is also the same as saying that we want to get the exact propagator for the fermion. So what's the structure? Let's write, so we are going to proceed by writing a self-consistency equation, sometimes called Schwinger-Dawson equation. So if this is the exact propagator, we are going to organize the contributions by separating the 1pi contributions and we are all very good at summing geometric series, and as a result we know that this gives the following result. It gives the first piece divided by 1 minus the 1pi ball with the second arrow, right? Okay, so we found the exact propagator in terms of this 1pi blob, but okay, we have this just gives something difficult in terms of something difficult. To close the equation, we need to write down another condition, and the right equation is this. So the 1pi diagram can always be this 1pi diagram. We can always write it as a gluon propagator with inside the exact propagator of the fermion. Okay, so that's what allows us to close the two. Okay, you see that this diagram is indeed 1pi because we have the gluon propagator and an exact propagator of the fermion. Okay, and we cannot cut any line and disconnect it. Okay, questions about this? Okay, of course this is at large n. Okay, this is at large n, otherwise we would have also additional contributions. And you can sort of understand from this structure that what we are doing is resumming the rainbows, right? It's like, imagine here we put the resummation up to a certain point, and then we are adding just something else outside. Okay, so this structure is what we need in order to resum all the rainbows. So now let's turn these drawings into some equations. So the equations coming from this are, so the gray blob we're going to write it like this. Yeah, sorry, I chose a bit of a weird order to write these two things, but and the 1pi is just what I called I gamma of k. Okay, so far I implemented this first constraint. Okay, I implemented this constraint because I've written, I have called the 1pi diagram gamma, and then if you just plug it inside, you write here the propagator, the three-level propagator that we have written. Here we write gamma times the three-level propagator. You massage a little bit, you do some algebra, and you get this. Okay? So far it's just a definition for this 1pi blob. And now the interesting thing is to write down this equation and try to solve it. Okay? We need to write down that one. So let's write down this. So on the left-hand side, we have, again, our I gamma. Let me call it of P. So let me put some momenta here. This is going to be called P enters and P exits. And then I will call this guy on the gluonic loop, on the gluonic line, I will call it K. And then this is P plus K. And this is P plus K. So what do we get? We get an integral. We have a loop, right? So since we have a loop, we have to integrate over. We have to integrate over the momentum K. So that's the equation star. We have to integrate over the K, and then we have minus G squared divided by K minus squared from the gluon propagator. We have a factor of n. I don't know why I put this parenthesis, it's useless. There is a factor of n from the closed loop, okay? There is a factor of n. Then there is 2i squared from the two vertices. So let me write this. This is the gluon propagator. This is the closed loop. And this is from the vertices. And now we need to write the exact fermion propagator. Right? The exact fermion propagator, we just wrote down an expression, is I k minus plus p minus divided by m squared plus, let me collect k minus plus p minus, and then I have this structure, 2k plus 2p plus minus gamma p plus k. Okay? This looks a pretty hard integral equation, right? But actually it's not hard. Now we're going to see that it's not so hard. So, to see that it's not hard, so first of all, let's treat k plus and k minus. We have to do this integral over, right, the two-dimensional space. Let's treat k plus and k minus as independent. So this requires us to go to Lorentzian. Okay. If we are in Lorentzian, this we can literally rewrite as an integral in dk plus dk minus, right? They are just two real components like any other. And when we go to Lorentzian, there is another thing that we have to do. We need to remember the I epsilon prescription. So this is going to be surprisingly important in our calculation. So we need to put this minus I epsilon, okay? This is going to be very nice, for it simplifies a lot. And now, what is the observation? Once I integrate in k plus and k minus, look at what I have here. You see that k plus only appears in this combination. Sorry, I meant p plus. You see, p plus only appears in this combination. So by doing a shift of the integration variable, k plus, I can completely reabsorb it. Is it clear? So as a result, this gamma cannot depend on p plus. It's going to be only a function of the k minus, of the p minus momentum. Is it clear? So just by a change of variables, I convince myself that gamma only depends on p minus. And now I need to, so let's put together all these things. I wonder, okay, so what did I do? I brought this I on the other side, and I get a minus I. Then I have a let's see. I have a minus 4 from here, becomes a plus 4, and then I have a minus I, okay? So let me put this factor together and write minus 4i g squared of n, okay? Just some algebra, I collected some factors. I need to remember that I need another minus I from Lorentzian, from going to Lorentzian. Okay, so far I was doing stuff in Euclidean, but now I want to go back to Lorentzian, so I get another I from the weak rotation. Then I have a 1 over 4 pi squared. And what do I have? I have an integral in dk minus of k minus plus p minus over k minus squared. This is the Gromb propagator. And then I have an integral over k plus. Now that's the magic, that's where the magic happens. Let's look at this integral. I have m squared minus I epsilon minus k minus plus p minus gamma k minus plus p minus. So I need to continue write this denominator here. So let me continue here. I continue the denominator, and the other term was plus 2k plus k minus plus p minus. Okay? You see what I did? I reabsorbed this p minus, this p plus, I reabsorbed it inside of k. Is it clear? So since I reabsorbed it inside of k, now my whole dependence on the integration variable here in this second integral, the integration variable only appears here. Is it clear? Okay. I mean, it's not so important that you follow all the factors, because then the factors you can also find on the references, but I just want to tell you the idea of the calculation. So, and also the factors, I might make mistakes myself. So now, the magic is that this integral turns out to be independent of whatever function gamma we put inside, okay? So that's what allows us to solve the first part of the problem. That's what allows us to solve the first part of the problem. And let's see why. Though this is a little bit of a complex analysis. Yeah, I think this is the oldest. Let's do a little complex analysis. Okay, so the first thing you might say is that this integral is divergent, right? Because we have a k plus in this denominator, and then when k plus is very large, you are integrating dk plus over k plus. So it has a logarithmic divergence. But okay, this is just a UV divergence, and we never stopped in front of a UV divergence, and we're not going to do it now. So for that purpose, we're just going to put a UV cutoff, right? And so let's just write a simplified version of this integral. So this integral that we are computing here, you can think about it as an integral from minus some cutoff to plus some cutoff, okay? I'm going to put some cutoff in my variable of dx, let me call it x, the integration variable. And then we have 1 over something linear in x, you see, there is just the variable x appears linearly. So there is ax plus b, some constant, minus I epsilon. Okay, that's the form. And basically our goal is to show that this is independent of b, the result. So if we show that it's independent of b, we win. And a and b are real. How do we compute this? Well, we can do it in many ways, but for instance, one way to do it is to do, I like to do it like this. I do a change of variable. Okay, let's do a change of variables. I go to 1 over x, basically. And this now, it splits into 2, right? I'm going to have an integral that goes from minus 1 over lambda to minus infinity. So this is the 0 minus region for the variable x, becomes minus infinity. And then I have another piece of the integral, which goes from plus infinity to plus 1 over lambda. And this is the 0 plus region for the variable x. And then I have a minus 1 over y squared for the Jacobian. And my linear thing becomes 1 over a over y plus b minus I epsilon. Could be that there are simpler ways to compute this integral, but that's the one I like. And now, you see, in this way, the cutoff now becomes something that cuts away a region around the y equals 0. Okay? So this is basically like computing an integral with the Cauchy principal value. We have divergence in 0, and we are doing a Cauchy principal value. So we have this kind of integral of 1 over y divided a plus b minus I epsilon y. Okay? Are there questions about this so far? So now let's look at this in the complex y plane. What should I erase? I think I should erase that one. Let's look at this in the complex y plane. And you see I'm cutting off this part with my cutoff, and then I'm integrating here and here. And when do I have poles in the complex y plane of that function? I have a pole in y equals 0, okay? And the other pole is just in, if you do the calculation, is in a over B plus I epsilon A over B squared. Okay, that's where the other pole sits. Crucially, the crucial thing is that the sign of this imaginary part only depends on the sign of A. So we are going to have a pole here when A is bigger than 0, and some pole here. It doesn't matter where exactly. The only thing that matters is whether it's above or below. And the pole here when A is smaller than 0. Right? Okay, so now what do? We want to do as least as like the smallest amount of calculations possible. So when A is positive, we are going to close with some contour in the lower half plane. Okay, so we pick this when A is positive in such a way that we avoid our pole, and when A is negative, we are going to close with this. Okay. So in both cases, please tell me if it's not clear what I'm doing. So I want to avoid the pole. So depending on when the pole is, I close on the opposite side. I didn't want to erase this. Too late. Very sad. Extremely sad, but okay. So now the arcs at infinity vanish. Okay, the arcs at infinity vanish, and so I'm left with the following answer for this integral. I get minus this small arc around the origin, okay, when A is negative, and I get plus this small arc around the origin when A is positive. You agree? That's the only thing that's left. Because if I close the contour, I find 0. I don't have anything inside. The arc at infinity is 0, so I'm only left with these two guys. And so what do they give me? So this one, you see, it's going clockwise. So with the minus in front, it's going to give me pi I times the residue at y equals 0. And this guy is going counterclockwise. Why did I put a plus here? This was also a minus, sorry. In both cases, I need to subtract the arcs. Sorry, I made a mistake in here. And this is going to give me minus pi I times the residue at y equals 0. And you see that the residue doesn't know anything about B, because to compute the residue, we need to compute this guy. We need to compute this at y equals 0, no? And so finally, we can write down our answer, and our answer is pi I times 1 over A when A is positive, and minus pi I times 1 over A when A is negative. So we are very happy. We got that our result for this integral is I pi 1 over absolute value of A. So if you remember, our gamma, the complicated function that entered our integral equation, was completely inside B, right? But we got that this integral, when we put this UV cutoff in this way, and to regulate it, we get this answer, which, by the way, doesn't depend on our UV cutoff, and is completely independent on B. So we are extremely happy because our equation became very easy. Our equation became extremely easy. we get now gamma of pi minus, plug in the result of the k plus integral, it becomes I g squared n divided by pi squared. Again, don't pay too much attention about the factors, because who knows how many mistakes I'm making. K minus plus pi minus divided by k minus squared. And here we plug our answer. Our answer, you see, I have to put I pi divided by the modulus of the vector, and the vector was a wait a second. It should be k minus plus p minus, right? That's what we get. I'm just confused about something. Give me a second. Ah, no, with the two. Yes, right? Okay. Now, this is our answer. And we can rewrite it. We can rewrite it just as follows. As minus g squared n over 2 pi times an integral in the k minus, okay, of the sine of k minus plus p minus divided by k minus squared. Okay? Tell me if you agree. I just did the simplification of the... Now, we were happy, but now we discovered something a bit concerning, which is that if you look at this integral, you discover that in this case it's divergent when k minus is 0, okay? So previously we had a divergence which was for large k plus in the previous integral we computed, and that doesn't scare us because we are used to deal with UV divergences in quantum field theory. This, however, is an IR divergence, okay? So when you see an IR divergence, typically it means divergence, it means that you're doing something wrong, okay? It means that something is wrong. And however, if we think about it a second more, we realize that what we're computing here is a propagator for the quark, right? The quark by itself is not a gauge invariant particle, right? It's the field psi is not gauge invariant, so it doesn't carry by itself any physical information. So the way we are going to proceed is that for now we're just going to put by hand some IR cutoff, and our hope is that when we pack everything together in our calculation, this IR cutoff should disappear when we get to the actual mass of the mesons, okay? Because the mass of the meson is supposed to be something physical. So for now we are going to do something which is like this IR divergent. So we regulate it by explicitly cutting off the region of small momenta. We introduce this IR cutoff lambda. We introduce an IR cutoff lambda, and then if you cut it off in this way, okay, this is now an elementary integral, right, with this cutoff. It's just a bit of a boring elementary integral because you need to be careful of whether p minus is positive or negative. But okay, after you spend some time with this boring integral, I will give you the answer. You just get minus g squared over n divided by pi, and you get sine of pi minus divided by lambda. So here is our IR cutoff, right? Our IR divergence. When lambda goes to 0, this explodes. Minus 1 over p minus. Okay? So, maybe before we go to the break, just to close this part, let's just write down the exact propagator of the quark that we got. We computed this gamma. And now we can write down the exact propagator of the quark. So the exact propagator of the quark is as follows. We put it in the denominator, right? We had that gamma in the denominator. So this is the exact propagator at leading order at large n. It's minus I k minus delta ij. There is no reason to put one up. Delta ij. And then we have mi squared plus 2k plus k minus. Then we have to plug that multiplied by a power of the momentum, okay? So it's that evaluated at k multiplied by k minus. So you see, when you multiply the second piece, you get just a constant here in the denominator. You get g squared n over pi. Okay, I'm just plugging in the previous formula, so we don't have to comment much about it. But then, unfortunately, we need to live at the moment with this weird IR divergent piece. And then there is the minus I epsilon if we are doing Lorentzian. And so the further comment is that this quantity, now it's very natural to put it together and call it some renormalized mass of the quark. And let me introduce a notation. So this whole thing we are going to call Si of k. You see, and then we go for real, like this, if we set this lambda to 0, it's a bit like having an infinite mass for the quark. So heuristically, if you wish, you can think about it as saying that really the quarks need to be, they cannot be like freely propagating particles, they need to be confined inside mesons. And that's the physical significance of this IR divergence that we are finding. Okay, so in the afternoon we are going to go and resum also the ladders.